In this video, I will make end-to-end encrypted communication between two Arduino Nano boards. I will use the Diffie Hellman key exchange algorithm to generate a shared secret between them. So if you have no idea of Diffie Hellman, then definitely check out the first part of this video series. I'll put the link in the description and also in the card somewhere over in the top right. And yes, the last video was not the best quality and I really apologize for that. So here is a quick recap of the last video and also the basic idea of the project. So we have these publicly known numbers which are G and N, where N is a prime number. Okay, so yes, 1 should be less than G should be less than N, because if G is 1, then 1 raised to the any number x will always be 1, right? And so 1 mod N will always be 1, okay, because N is prime. Okay, and N is prime and N cannot be equal to, let's say, 1, right? Okay, you get the point. Now if G is N, then G to the x mod N will always be 0, because if G and N are equal, then G to the x will be a multiple of N, so this will be 0. And if G is greater than N, then, well, in modular arithmetic, things start to repeat and it will not be computationally and efficient. So basically, let's say N was 7 and let's say G was 2. So G to the x was 2. I'm taking arbitrary numbers and this is, let's say, N. If you do the modulo, you get 5. But if you take if you take 12 and you do mod 7, this is also 5. So what I basically wanted to say was that after 7, these remainders will start to repeat. So it's no point doing that, and it is really computationally intensive to choose big numbers. So right, okay, so we don't want it to be too big, okay, because N is a big prime number. Okay, so next. So next here we have, wait a second. So next slide, please. Yes. So here we have our Alice and here we have our Bob. So what Alice does is that she takes a number A randomly. Okay. She raises G to the A and does mod N. Whatever the result is, she sends it to Bob. But Bob does is, Bob randomly chooses a number B, raises G to the B mod N and sends it to Alice. Okay, so next what they do is that what Alice does is, this is what Alice does. So Alice received this G to the B mod N. She raises it to her private number A and does mod N on it. And this is what Bob does. What Bob does is that he takes G to the A mod N that was sent by Alice. He raises it to B, which is his private number only known by him, and does mod N. And this is equivalent to G raised to the AB mod N. You can think about why it is yourself. And in case you are having trouble, then definitely comment and I will make a video on it. So here I have a very fun little experiment. So we take G and N, and in this C program I have taken A and B, which were the private numbers of Alice and Bob, but we are going to do a fun experiment with these. So we are writing them in this same program. So in the main function, first we do Bob's message for Alice. Basically here message means we are calculating the shared secret. Okay, basically, okay, I mean you get it. So yeah, G to the B mod N is what Bob does for sending to Alice, and G to the A mod N is what Alice does for sending to Bob. Everything is alright till here. Next, to get the shared secret, Alice raises what Bob sent to the Bob raises what Alice sent to the B and does mod N, and Alice raises what Bob sent to A and does mod N. Now, the shared secret calculated by Bob shall be the same as calculated by Alice, and this should be equal to G to the AB mod N. Okay, so here first we have G and N, we will not change, these are 5 and 23, and we take A as 3 and B as 2, so it should work normally. Yeah, so it run normally. It's saying to use LLU because it's a long integer. It's a 64-bit integer, but as we are doing mod 23, the result will never be more than 23 mod n. Anything mod n cannot be greater than n. So basically this is alright, don't worry about this warning. So we get G to the power B mod n to the A mod n to be 8, G to the A mod n to the B mod n to be 8, and G to the AB mod n to be 8. Okay, alright. If I turn B to 4, and again the output must have come below here. Yeah, so G to the A mod G to the B mod n to the A mod n equals 18. G to the A mod n to the B mod n is also 18. G to the AB mod n is also 18. So let's do one more thing. Let's make A to be 5 and B to be 6. Now let's see what happens. And wow, what's happened? G to the A mod n, G to the B mod n to the A mod n is 16. G to the A mod n to the B to the B mod n is also 16, but G to the AB mod n is 5. Now why is that happening? Okay, so the maximum value a 64-bit. So first of all, in most programming languages, the maximum size of a number that's allowed is 64-bit, okay, or 8 bytes, right? And when we calculate this, G to the A asterisk B, okay, this should be in brackets because pedmiss, and G to the AB is 5 times 6, which means 5 to 30, and let's see what 5 to the 30 is. So 5 to the 30, let's see what it is. It is a 21-digit number. You can see it is 9 point this thing E20, meaning into 10 to the 20. So 9 is the first digit into this. And what is the maximum value? So this is a 21-digit number. So this is a 21-digit number. And what is the maximum value a 64-bit number can be? Let's see. So if there is a 64-bit number, so if there was an 8-bit number, so there will be 8 bits, 1 2 3 4 5 6 7 and 8. So this bit can be either 0 and 1. Given this bit, this can be either 0 and 1. So the maximum possible value will be 2 to the 8, right, for an 8-bit number. Because given this value can be a 0 or 1, this value can be a 0 or 1, this value can be 0 or 1, you get my point. And given this value being 0 or 1, this value can either be 0 and 1. So there's becomes 2 times 2 times 2 times 2 times 2 times, because for every possibility there can be 2 other possibilities, and for every bit there are 2 possibilities. That's why we are doing this. I think it's pretty self-explanatory, but if you didn't get it, then write it in the comments and I can make a video on it. I think there are plenty of videos and articles like on Khan Academy, so you can definitely check it out. So the maximum value and 64-bit integer can have will be 2 raised to the 64 minus 1, because because maximum why minus 1, because we consider this 0 also. So the maximum number of permutations will be 2 to the n, but the maximum value will be 2 to the n minus 1. So what can be the maximum value? So 2 to the 64 minus 1, you can see it's a 20-digit number. So it's a 20-digit number. That's why if you try to calculate g to the ab mod n directly, in this intermediary step over here where you have to calculate g to the a and b, the precision of the computer fails. Basically the memory overflows, right? And most programming languages don't allow more than 64-bit in values. Okay, so yeah, that's why we are seeing this error. I hope this was a fun example. So here is the schematic for the project. The pin D3 of Alice is connected to the pin D4 of Bob. The pin D4 of Alice is connected to pin D3 of Bob, and ground is connected to ground. But if you have connected both of the microcontrollers to the same computer using the USB cable, then it is not necessary to connect their grounds together. So let's quickly understand how strings work. So 8 bits, usually called a byte, is the smallest addressable unit of memory, i.e. every memory address points to 8 bits or 1 byte on our microcontroller and most computers as of now. So as you might know that every character on our microcontroller is represented using 8 bits, and they are represented as their ASCII value or American Standard Code for Information Interchange. So how strings work? String is just a set of characters, and in memory it is represented as an array, and an array is basically a set of contiguous memory locations. I mean, every location is one after the other. So if I want to store this string or this message hello, then and in an array of 8 characters, so every character, as I told you, is stored in form of its ASCII value. So let's say our array starts at location 100, so h will be stored at 100. Every location is, I said, 8 bits, and so that's why every character is also 8 bits, so every character takes one location. So basically H is capital H is represented as 72 in the ASCII table. So at memory location we have H as 72. Similarly, capital E is denoted as 69. capital L is denoted as 76, and O is represented as 79 in ASCII table. So that's why these are stored from the starting address 100, 101, 2, 3, and 4. And after this \0 is automatically added after uh, after any string. This \0 is added. It's a part of string, and what it helps us in is it helps us know where does the string ends, because as you can see, our string is just a block of continuous memory locations, and if there is a block of continuous memory locations and we know where it starts, but we have no way to know where it ends. So this \0 with whose ASCII value is just 0 helps us know that hey, our string ends here, and this 0 is different from the character 0 whose ASCII value is 48. It is not that, it's the \0 whose ASCII value is actually 0. It's a character. Okay, so its ASCII value is actually 0, the number 0, right? So yes, so you get my point. So so if you want to allocate a string, let's say car, then uh, then to store this you will need actually 4 bytes, and if you allocate an array called C, then you cannot keep the size as 3, you need to keep the size as 4. Why? Because of the simple reason that you have this extra character \0 which tells us where does our string end, and this is how we know where our string ends. And the com.write function, in which we pass our string to send it from Alice to Bob or Bob to Alice, also uses this \0 to find where our string ends. That's why when we will do the encryption, maybe we shift all these by the shared secret. Let's say 72 becomes 74, 69 becomes 71, and if the shared secret was, let's say, 2, and we shift all of these, but we will not tamper this 0, because if we tamper this 0, our com.write function will have no way to understand where our string ends. Don't worry if you didn't understand this, we will see this in code. Okay, so I hope now you understand how string works. So here on the left we have the code for Alice, and on the right we have the code for Bob. I'm using platform IO for writing the code and uploading it to the microcontrollers. You can use the Arduino IDE to just copy and paste these things into the Arduino IDE and it will work the same. Okay, so right. So first, so in platform IO, you have to include this header file arduino.h to use the Arduino libraries and functions that Arduino framework provides. In the Arduino IDE, this happens automatically. So in the Arduino IDE, you may delete this line, but even if you don't, things won't change. It will be included automatically. Next, we include the software serial library because we will be using a software serial port, not the hardware serial port for serial communication, so that we don't have to plug and unplug cables during upload. Next, we define these, as I told you, G and N, which are publicly known. So we define these constants on both sides. Okay. Next, here Alice chooses her number, which is A. In this case, we choose 5, and for Bob, we choose this number to be 6. Next, we define these RX pin and the TX pin of both Alice and Bob, which is on both sides 4 and 3, and this is what the software serial port. Okay. Next, I've defined this power function because the power function was giving errors, and also it returned double, and it was causing troubles even after typecasting. I don't know why, and I will see. And here, so I defined my own power function. It just takes a number and an exponent and then raises this number to this exponent. It's pretty simple. And then we initialize our software serial port. I call it COM on both sides, and we pass in these constants RX and TX, which is the RX and TX pin. Next, I defined this U means unsigned integer of 8 bits, basically a 1 byte shared secret. In case you don't know this notation, U means unsigned, I means integer, and um, 8 8 means it's an 8-bit integer, and underscore T means type. So basically it can store 8 bits. It's right. And similarly, this UINT64T means it's an 64-bit unsigned integer. Unsigned means it can only take 0 and positive values, not negative values. Okay, so this can go from 0 to 255, and right. Okay. Now next we define our string here. Jar message for Bob. Message from Bob. Here we'll store the message that comes from Bob. And similarly here, message from Alice, the message that will come from Alice. Now we, in the void setup, we wait for 10 seconds so that things become stable as we plug in and open the serial monitor. Then we initialize the serial port with a baud rate of 9600. Okay. Next, we also start the software serial port at the baud rate of 9600 on both sides. Next, we print to the serial monitor that Alice online and Bob online. Then we wait for 500 milliseconds for string for things to get stable. Next, we have this serial.print line. Alice is transmitting, and we write Bob is receiving. Again, here we are waiting for 3 seconds, and after 3 seconds, we will write this number. 3000 milliseconds is 3 seconds. And then here, after Bob is receiving, we wait for 500 milliseconds, we do nothing. Next, we start this while loop, while com.available equals to 0, meaning while there are no bytes coming in the com port. Basically, we are constantly checking while no bytes are available from Alice, wait, and Alice will send the bytes after this delay of 3 seconds. Okay, so as 3 seconds pass, what will happen is that this will become non-zero, basically 1 byte it will be. Next, we do what is we in this shared secret variable, we raise it to we read whatever was sent by Alice, and it was just to block the code till the till something is received from Alice. Next, we raise whatever Alice sent to the B, which is Bob's private number, and we do mod n. So here I have written also, read what Alice sent. Alice sent this number G to the A mod n. Remember, we don't know the value of A inside Bob, so we just got the solution to this expression, and we raised it to the B, and then we did mod n. So basically this was G to the A mod n. This is something that Alice sent. We raised it to the B, and we did mod n, and it is the same as G to the AB mod n, right? Next we write and next in Bob we write serial.print ln shared secret is, we print the shared secret. And next what happens is that here after this Alice wrote sent to Bob, and then what happens is we wait for we wait for 1 more second, and then Bob is transmitting. We wait for 3 seconds, and we transmit the message from Bob to Alice. Next, what happens is Alice prints. Alice is receiving. She waits for 500 milliseconds. Next, we do while com.available is equal to 0, meaning while there are no bytes available from Bob, we wait, and after that you can clearly see that Bob is sending G to the B mod n to Alice. we do com.read, which will receive our G to the B mod n. We raise it to the A, and then we do mod n. So that is something we stored in the shared secret here also. And as you can see the comment, read what Bob sent G to the B mod n, raise it to the A, and do mod n. So we do that here. Next, we print to the serial monitor shared secret is shared secret. Okay, and then we wait for 1 second on both sides, and now Bob wrote to send to Alice, and then we will wait for 1 second both sides for things to become stable. And yes, next in the loop we do what? We say char message for Bob. This is the message we are going to send, is hello Bob, HELLOBOB. So these are 9 characters, you see, HELLO space BOB, but still we declared it as a 10 character array, because after this hello Bob, the \0 character will be added automatically. Okay, this will be added automatically, you see. Now we do encrypting message for Bob. It is something Alice writes. Alice waits for 500 milliseconds. Next, again we take an unsigned 8-bit integer I equals to 0. I is less than 9, I plus plus. Now you can see I am taking here I is less than 9. So I is less than 9 clearly means it will go from 0 to 8. But you can see that our array 0 to 8 will equals only 9 characters. But as you can see, our array has 10 characters. The reason we are not tampering that \0, because the \0 is how computers know that it's the end of the string and we have to stop transmitting. That \0 at the end of the string is never ever transmitted. Okay, okay, I will show you that further, but you can clearly see we are shifting every character by the shared secret except the last null character. Okay, that \0. Next, after this is encrypted, we print sending, wait for a second, then we send it to Bob. Okay, now we wait for 3 seconds. Now here is the thing, if we tampered, let me write it here also, if we tampered the \0, this com.write function here will have no idea of where to stop, because I told you string is just a set of contiguous memory locations, and if there's no null character, it will just transmit the whole memory. It will have it will have no idea where to stop transmitting bits. So that \0 is never transmitted. When this com.write function reads that \0 in this string, which was added automatically after this string, it says, hey, it's time to stop transmitting. That's why this thing is never tampered, as I told you. Next, we do sending, after we have sent the message, what happens here? Next, now I know that the maximum size, actually you can keep the size as long as you want, but I have just used 9 here because I know how long the message on both sides will be. You can keep it as 100 characters or whatever. Okay, just take 1 extra character for that null character and things will happen normally. And okay, and see, and even as I told you that one more thing I would like to mention here, if I had an array message, I hope it is visible to you, I'm writing, of 100, okay, even 1000, and even if I use just five characters, then the \0 will be added right after this. It will not be at the last index of the array, it will just be here. So the size is it doesn't matter if you choose a bigger array, because bigger arrays don't cause any problems. Even if the array is of 1000 characters, and even if you store only 5 characters, the sixth character will be this \0, not the last character. So yes, you can take the array size as big as you want. Now here's what we do. We know that the message that Alice is going to send is just 9 bytes. So com.available reports us how many bytes are available on our software serial port. So we wait for, as you can see in the comment, also wait for Alice's message to arrive, which is 9 characters, and one character is 1 byte long, so that we wait till there are 9 bytes available on the uh, port. Once they are available, what we do is we again run a loop here from 0 to 9, so 9 characters. What we do is we, in message from Alice, we store com.read. Com.read just returns a single byte in a single byte. So the message is to be read from the first byte to the last byte, byte by byte. So it returns a single byte. That's why we are running this loop. What we do is we read this byte, and here we added the shared secret, so here we subtract the shared secret. And you have seen how this shared secret is generated above in the setup function. So next we print the message from Alice. We wait for 3 seconds, and then we write message for Alice. Wait a second, it should be message for, I guess. Oh, it should be, yes, yeah, it is Bob here, so it's right. So here we print what the message that Alice sent. Now we are writing the message for Alice. Here we are on Bob. So this is 12 characters long, 11 characters, 5 space 5, and the \0. Next we write sending encrypting message for Alice. We do the similar kind of encryption. We shift all the characters by the shared secret. Next we write sending, we wait for a second, and we write the message for Alice to Alice. And here we are back in Alice, right? So now let's see. So yeah, so here on Alice, we first wait for message from Bob. So she writes waiting for message from Bob. Next we wait for 100 milliseconds. Next we have this this while loop, which checks till the number of bytes available becomes 11. So 11 bytes long is the message. I told you that \0 is just for this com.write function. Know the end of string. The 12th character is never sent. Okay. Next we do the similar kind of decryption, and we print the message. Okay. So yeah, this is the code. Now let's see the practical implementation of it by uploading it to the microcontroller. That's okay. Next I'm going to show you that. Okay, so now is the time for the practical demonstration. So on the left we have Alice, and on the right we have Bob. Their grounds are connected together, although that's not necessary because both of them are connected to the same computer. And the pin D3 of Alice is connected to pin D4 of Bob, and pin D4 of Alice is connected to pin D3 of Bob. Okay, and that is for the software serial port. Okay, so here in platform IO, on the left we have the code for Alice, and on the right we have the code for Bob. Once again, you can open this in Arduino IDE to just, instead of this main.cpp, you can rename it to main.ino, or just copy and paste this code into the Arduino IDE. Okay, now how do I know that this left one is Alice and this right one is Bob? I have in platform IO project, this platform io.ini file, in the platform io.ini file, I've added this command, this attribute here, upload port is equal to USB serial 140 and upload port is equal to USB serial 130. So that's why I know. Yeah, so yeah, that's how I know that which one is Alice and which one is Bob. Now in Linux and Unix based operating systems like Mac OS, this this COM port will look something like this, and in Windows it will be like COM3, COM4, something like that. But if you're using the Arduino IDE, you can use the toolbar here to configure the COM port, and you can connect one Arduino first, get its COM port, select it, and then use the other Arduino. And okay, so next what we'll do is we'll compile by clicking on this tick button in the bottom corner, and then we will click upload buttons. And since we are using a software serial port, not the actual serial port, we don't have to remove those lines during upload, because the hardware serial port is this port which is also used for uploading the code to the for burning the code to the chip basically. So next we'll launch the serial monitor. To launch the serial monitoring platform, you need to click this plug button, and on the left we want this serial 140. So we will enter the port number, which is 3 here, and on the right we want this 130 whose number is 2 here. We'll quickly reset these microcontrollers so that everything gets stable. And now just let's see how are they communicating. So we are waiting for their messages to come. Alice is online, Alice is transmitting, Bob is receiving. Yeah, Bob got the shared secret is 16, and Alice also got the same shared secret. Now they're encrypting and sending messages. Yeah, and they will keep on doing this in the infinite loop. Beautiful. Okay, so this was the practical demonstration. Thanks for watching.